Disk scheduling is like a traffic controller for a busy highway of data. Modern operating systems have many programs asking the hard disk or solid-state drive to read or write at the same time. If the disk answered requests in the order they arrived, the read-write head would jump back and forth all over the platter, just like a school bus that drives to the farthest stop then immediately back to the nearest one, wasting fuel and time. By deciding the order of service, the operating system can reduce the time the head spends moving, seek time, lower the waiting time for each request, and increase the overall throughput of the system. This is essential because slower disk response slows down the whole computer, just as a slow kitchen delays all orders in a restaurant. A disk operation consists of three measurable parts. Seek time, abbreviated TS, is the time for the read-write head to move from its current cylinder to the target cylinder. It is roughly linear with distance. TS equals alpha times the absolute value of C current minus C target, where alpha, measured in seconds per cylinder, depends on the drive mechanics. Rotational latency, abbreviated TR, is the waiting time for the desired sector to rotate under the head. On a disk spinning at R rotations per minute, one full rotation takes 60 divided by R seconds. The average latency is half of that. TR average equals 30 divided by R seconds. The worst case is a full rotation. TR maximum equals 60 divided by. Transfer time, abbreviated TT, is the time to actually read or write the data once the sector is under the head. If the data block size is B bytes and the disk's transfer rate is V bytes per second, then TT equals B divided by V. The total service time for a request is T equals TS plus TR plus TT. Scheduling algorithms try to minimize the sum of all TS values, because TR and TT are mostly fixed for a given request size. FCFS, first come first serve, works exactly like standing in a line at a ticket counter. The first request that arrives gets served first, then the next, and so on. Algorithm steps is 1. Keep a first in first out queue of incoming input-output requests. 2. When the disk becomes free, dequeue the head of the queue and service it. 3. Repeat. Numerical examples. Assume the head starts at cylinder 50 and the request queue and arrival order is 90, 10, 70, 30. The head moves 50 to 90 equals 40 cylinders. 90 to 10 equals 80 cylinders. 10 to 70 equals 60 cylinders. 70 to 30 equals 40 cylinders. Total distance equals 220 cylinders. Average equals 55 cylinders per request. Performance characteristics. Simple to implement, fair, no request is skipped, but can be very inefficient because the head may travel long distances back and forth, high average seek, high worst case. It works okay when requests are already roughly sorted, or when the load is very light. SSTF, short for shortest seek time first, always picks the waiting request that is nearest to the current head position, similar to a delivery driver who always serves the closest house first. Algorithm steps is: when the disk is idle, look at all pending requests. Choose the request with the minimum absolute value of C current minus C target. Service it, update the head position, and repeat. Numerical examples. Same start at 50, Q90, 10, 70, 30. Nearest to 50 is 30, distance 20. Service order becomes 30, 10, 70, 90. 50 to 30 equals 20. 30 to 10 equals 20. 10 to 70 equals 60. 70 to 90 equals 20. Total distance equals 120 cylinders, average equals 30 cylinders, about half of FCFS. A starvation issue. If new requests keep arriving near the current head, far away requests may wait indefinitely. For example, a request at cylinder 200 might never be served if many requests keep appearing near cylinder 0. This is called starvation. Analytical comparisons. SSTF reduces average seek time compared to FCFS, but does not guarantee fairness or bounded worst-case latency. Scan elevator disk scheduling moves the head back and forth across the disk like an elevator that travels from the bottom floor to the top floor, serving all requests in its path, then reverses direction. Mechanics. Step 1. Choose a direction. Upward equals increasing cylinder numbers or downward. Step 2. Service all requests in that direction in order of increasing cylinder number. Step 3. When the last request in that direction is reached, reverse direction and continue. Numerical example. Start at 50, direction equals up, Q90, 10, 70, 30. Sorted list equals 10, 30, 70, 90. Moving up. Service 70, first greater than or equal to 50, then 90. At the top, cylinder maximum, assume 100, reverse. Service 30, then 10 on the way down. Travel distances. 50 to 70 equals 20, 70 to 90 equals 20, 90 to 100 equals 10 to edge, 100 to 30 equals 70, 30 to 10 equals 20. Total equals 140 cylinders, average equals 35. Edge case handling. If there are no requests ahead in the current direction, the head simply reverses immediately, no wasted travel to the edge. Some implementations stop at the last request instead of the physical edge. This variant is called look. Throughput. By sweeping the disk continuously, scan reduces the variance in wait times and avoids the starvation problem of SSTF, while still keeping average seek lower than FCFS. C-scan, circular scan, is like a bus that only travels in one direction around a circular route. It goes from the lowest to the highest cylinder, serves requests on the way, then jumps back instantly to the start without serving anything on the return. Mechanics. 1. Choose a direction, usually upward. 2. Service all pending requests in increasing cylinder order. 3. When the head reaches the highest cylinder, it quickly returns to the lowest cylinder, the reset movement, and starts again. Numerical example. Start at 50, direction up, Q90, 10, 70, 30. Sorted 10, 30, 70, 90. Service order, 70, 90, those greater than or equal to 50, then reset to 0, then service 10, 30. Travel distances, 50 to 70 equals 20, 70 to 90 equals 20, 90 to 199, assuming maximum 199 equals 109, reset 199 to 0 equals 199. But this movement does not serve any request and is usually not counted in average weight, 0 to 10 equals 10, 10 to 30 equals 20. Effective service distance equals 20 plus 20 plus 10 plus 20 equals 70 cylinders. Average equals 17.5 per request, much lower than scan. Uniform wait time property. Because every request sees the head pass once per full cycle, the maximum waiting time is bounded by the time of one complete sweep, giving more predictable latency. Performance figures. C-scan often yields the smallest variance in wait time and good average seek, at the cost of extra non-service travel during the reset, which is usually cheap because the head moves at maximum speed. Quantitative comparative evaluation. Algorithm average seek in cylinders, worst case seek, variance of seek, remarks. FCFS, average seek approximately 55, max distance equals 199 full disk. Variance high depends on request order, remarks simple but inefficient. SSTF, average seek approximately 30, worst case seek less than or equal to 199, but often lower because head stays near hot region. Variance moderate can be low for clustered requests. Remarks may starve far requests. SCAN, average seek approximately 35, worst case seek less than or equal to 199 edge to edge. Variance low, each request sees monotonic movement, remarks fair no starvation. C-SCAN, average seek approximately 18, worst case seek less than or equal to 199 plus reset travel, but reset not counted for service. Variance very low, uniform across cylinders, remarks predictable max wait time. Mathematical formulation. For a workload W set of C1, C2, Cn sorted as S1 less than or equal to S2 less than or equal to Sn, the average seek for scan when starting at head H and moving upward is average seek subscan equals 1 over n times open bracket open parenthesis sum over I, where H less than or equal to Si of Si minus H close parenthesis, plus open parenthesis sum over I, where Si less than H of Sn minus Si close parenthesis close bracket. For C-scan, the non-service reset distance is omitted from the average, leading to average seek sub C-scan equals 1 over n times open bracket open parenthesis sum over I, where H less than or equal to Si of Si minus H close parenthesis, plus open parenthesis sum over I, where Si less than H of Si minus 0 close parenthesis close bracket. These formulas show why C-scan typically yields the smallest average when requests are uniformly distributed. Explanation, practical selection guidelines and hybrid strategies. When to pick FCFS, very low I/O load, simplicity matters more than performance, for example embedded controllers. No extra CPU overhead. When SSTF is useful workloads with strong locality, many requests around the same cylinder, such as a database scanning a single index range. Beware of possible starvation. When SCAN fits best, general-purpose servers where fairness is required and the request pattern is mixed. It balances average seek and worst-case latency. When CSCAN is preferred, real-time or multimedia systems that need bounded maximum wait time for every request, for example streaming servers. Uniform service time across the disk is crucial. Look/clook, variants that stop at the last request rather than the physical edge, saving the unnecessary travel to the extreme cylinder. They keep the same fairness properties with slightly better average seek. Adaptive algorithms, modern operating systems may monitor recent request patterns and switch dynamically. For example, use SSTF when request density is high, fall back to SCAN when spread out. Some kernels implement deadline scheduling, combining a fast path like SSTF with a deadline queue to guarantee limits. Real-world considerations, solid-state drives have negligible seek time, so traditional disk scheduling matters less. However, the concepts still apply to request ordering for erase block management. For hard disk drives, the mechanical characteristics, alpha, RPM, dictate how much benefit you get from each algorithm. In practice, most modern operating systems employ a hybrid such as CFQ, completely fair queuing, which mixes fairness like SCAN, with priority classes or deadline scheduler that guarantees a maximum service time while still trying to minimize seek. Understanding the basic algorithms helps you tune these advanced schedulers for specific workloads.